Before I do that, some organizational issues. One is essentially all of you have at least one prelim this week, and the homework assignment came late. How many of you would appreciate an extension on the homework of this course until Tuesday? How many have no need for that extension? I think there are more of you than this that should be here. Okay, next. I would like to do a MATLAB catch-up, especially for the tutorial lessons 1 through 6. And I'd like to do it this weekend. I want to try and pick times, like Saturday afternoon versus Sunday afternoon. So here's don't care. First of all, everybody vote D or E so we can flush the thing out.
So wait, there is an exception?
I'll take the vote under advisement, taking into account the number of people who would like the extension and the number of people who would not like the extension. Any reasonable person who offers the choice and looks at a vote like that would not really have much choice in the response. Right? It would be a little fraudulent for me to be claiming to be seeking your opinion and not to respond to a vote like that. Okay, please vote D or E. Okay, let me just say simply, yes, we'll have an extension of the homework till Tuesday. Vote D or E. Take your clicker, press D or E. There's a way to do this. Okay. Saturday, Sunday, don't care. C is want to come, don't care, and D or E, you don't need the MATLAB tutorial on lessons 1 through 6. Saturday afternoon, Sunday afternoon, don't care, not interested anyway. Okay, now let's do, so this is close enough to equal, so I have to live with it. Now, let's do, can only make Saturday, can only make Sunday, can make both days. This is, I cannot come Sunday, I cannot come Saturday, I can come both days. Does it depend on the details of the timing? You tell me what details matter? Just throw out some numbers and you can only do it before 5. Any other people who have time restrictions?
After 1 Saturday.
It has to be after 1, and it has to be before 5. Okay, so let's assume it's between 1 and 5 on Saturday and Sunday. Can come Sunday but not Saturday. I mean Saturday but not Sunday. Can come Sunday but not Saturday. Can come both days between 1 and 5. The people with conflicts that cannot come, so this says that Sunday is a better day and you can't come Saturday. Now the people who cannot come Sunday here, are there any times when you could come Sunday? What?
Before 6.
We already said it's going to be between 1 and 5.
After 5. I agree.
No.
After 3.
What is the nature of the conflicts here? Can I just hear the kinds of things? Does anybody have some intuition about this, or should I do a detailed vote on the times?
How about 3 to 5?
Okay, tentatively we're doing 3 to 5 Sunday. 3 to 5 Sunday, you can make it. 3 to 5 Sunday, you can't make it. You don't care, you can't make it any of those times. Okay, we're aiming for 3 to 5 Sunday. People who can't come to that go to office hours or something like that.
In this room, right?
I'll announce the room. It probably will not be this room. And it's not going to be a lecture. It's just going to be question and answer demos. Just whatever your issues are. Any other logistics questions about the course? I don't know. Any other logistics questions about the class?
Do we have to stay the whole time?
Do you have to stay the whole time? No. Yes? You want it on North Campus? You find a room for me, we'll do it on North Campus. Email to me.
Libraries have it.
Hmm?
I don't think any libraries have that.
Find a room. I have MATLAB on my computers. What? You send me an email saying it's reserved and ready, and we'll do it there. Any other logistics questions? Okay. Mechanical engineering is about the mechanics of things. There are all kinds of things around. Some of those things are liquids. So part of mechanical engineering involves the mechanics of liquids. The simplest subject for liquids or gases is called hydrostatics. And we've done an introduction to hydrostatics. I hope most of you caught the basic ideas there. I think I will give an in-class quiz about hydrostatics next week, a brief quiz, so you should try to catch up and make sure you understand that. Now we're going to go on to another basic subject, which is mechanics of solids. So there's a whole course, in fact there's a whole sequence of courses that you will take if you're in mechanical engineering on mechanics of solids. And I want to do here a brief introduction, which also will get you partially lined up for the lab, which is today. So we have these objects, which are solid objects. Mostly when you think of mechanical engineering, you think of machines and things which are solids. And you'd like to understand how these objects work. Now, how do they work? They're just there. But when you're mechanical engineering, you have to think about, do they break? Do they bend? Do they stretch? Do they have friction? What happens when they bounce? And so on. So even one simple object is a thing which has, is a machine in itself. And the simplest way to think about things is the machine in itself is that it's a rigid object or a rigid body, which means all pairs of points between the distances between all pairs of points in the object stay constant in time. So all triangles remain similar to themselves as time progresses. The triangles you can draw between atoms. That's not good enough, because that doesn't tell you what's really going on inside, how the material is stretching, deforming, breaking, and so on. So you want to try to get a sense of when things will break, how much they stretch, and so on. And the simplest way to keep track of that is with the theory of elasticity. It's called theory of elasticity. It sounds fancy, which is to assume that the thing deforms a little bit, whatever that thing is. Maybe it's so little that you can't see it, and that deformation is proportional to the amount of load which is put on it. So what's that saying is that most solid objects are, if they go into deep Freudian analysis and think about what they are themselves, they are springs. Everything's a spring. Now, it's not really true that everything's a spring. Water's not much of a spring. Actually, when you compress water, it's just in compression it's sort of a spring. But liquids are not so much like spring. Pie dough is not so much like a spring. But most of the objects that you deal with in engineering for making machines and buildings and so on are springs. And what do you mean that they're springs? Just repeating, it means that they deform a little bit. The distances between atoms change a little bit. And the amount of change of that distance is proportional to the load on the structure. Okay, so now we want to try and develop that idea and think about what it means and build up some formulas and some kind of quantitative understanding of that idea. So in the background is this idea is that everything's a spring. And this is, of course, a lie, but it's a pretty good approximation for engineering purposes. Why do we care that everything's a spring? Is because sometimes you want to know how much a building, a machine part, deforms under load. And also, it's understanding that deformation that lets us figure out at least the first guess, the first approximation of when something will break. Okay, so we start out with this idea that everything is a spring. And then what do we mean by a spring? Well, the most simple picture of a spring is that you take a wire and you pull on it. And first you have this wire, then you stretch it, and initially it has some length which is called L0, which is called the rest length. Afterwards it has some length which is called L, which is the length after stretch. And how did you go about stretching it is you applied some tension to it. And we have this basic rule that the tension in the spring is proportional to the length minus the rest length. So what is this? This is called the stretch. How much the thing has gotten longer. This is called the spring constant. And this is what's called the tension. And in this case, it's a tension force in this sense that pressure is not really a force per unit area and tension is not really a force. Why not? Is because force is a vector. Which direction is the tension? To the right or to the left? Well, it's both. So tension isn't really a vector. The force at the right end of the spring is a vector, and the force at the left end of the spring is a vector, and tension is the scalar, which tells you how big that vector is pulling away from the ends. Or a tensor, as I said before. Tensor as in tension. That's the origin of the word. Okay, now I'm saying that everything is a spring. So let's just take a random thing. A random thing is I just got a coffee from the Duffield, is a coffee stirrer. So here is a typical machine part, a coffee stirrer. And my claim is if I take this coffee stirrer and pull on it, it stretches a little bit. I can actually, I think I can feel it deforming between my fingers, squeezing a little bit. And can you see how much it stretches when I pull on it? Okay, you can't. So does that mean it's not stretching? Okay, it's stretching a little bit. And this is what it's all about, is trying to think about those teensy bits of stretching. So here's the fact of the matter. Can you give me about half of that pile? The fact of the matter is that engineering materials like steel, wood, bone, rocks, aluminum, wood, by the time you can see that they're stretched, they're broken. So when we talk about this thing that everything's a spring, we're talking about everything's a spring, but everything is really quite a stiff spring. Nonetheless, we want to think about how much of a spring it is. Okay, so we're studying the deformation of this thing, and the deformations, the stretchiness of this thing is something which is so small you can't see it. Now, there are tricks that make it so you can see it, and we're going to talk about those tricks in about 15, 20 minutes. With this very same piece of wood, we can make it so you can see this deformation. Okay. Such an obvious trick, you're going to feel like it's not even a trick. There's even a trick for me to call it a trick, but you'll see how it goes. How much does it stretch when you pull on it? Any guesses? What? A millimeter. So how hard are we pulling on it? Well, you can only squeeze so hard with your fingers, and so your ability to pull on it is dependent just on the friction you can develop. Now, if you wanted to get a big tension on this, probably if you sat next to your neighbor and you each chewed on one end and got your teeth, you could pull with your hands. You could probably get a pretty big force. But with your fingers, you can probably only get, the best you could probably do is 5 or 10 pounds. Okay, so how much, so we say tension is equal to what's called 5, say, pound force as opposed to pound mass. And we're going to have to start worrying about units in this class for calculations. And this is going to go to a change of length. Now, what do we call this change of length? There's a change, and usually people use the symbol delta or delta L for this change in length. Those are two different symbols used for the change in length. Use that delta symbol for change. So this is going to go to some delta L, I prefer delta L of, somebody said a millimeter, somebody said a nanometer, which is, how do you spell nanometer? NM? Somebody said what else?
A micrometer.
Oh, micrometer.
That's what people get.
Now, there's other unit systems in the world. How about like 1,000th of an inch? What's the relationship between 1,000th of an inch and a millimeter? Does anybody know that? Does anybody know enough to tell me how many thousandths of an inch in a millimeter, or thousandths of a millimeter in an inch, or anything like that, if I just gave you 5 minutes and a calculator and you weren't allowed to use the web? Who knows enough to do that? Okay, so those of you who don't, you would like to be able to do that. Some number that relates inches to millimeters or meters from which you can figure this all out.
1.5.
What are some useful numbers? There are, let me just tell you some kinds of numbers that you should know. 39.37 inches is equal to 1 meter. Or, to go the other way, 2.54 centimeters equals 1 inch. Anybody know any other numbers to work out this conversion?
1 mile equals 1.6 kilometers.
1 mile equals 1.6 kilometers. Now, I'm assuming you know how to go between kilometers and millimeters and meters and so on. Everybody knows that. Does everybody know what a mile is in terms of feet and inches? Shh, you already said your turn. How many people know what a mile is in terms of feet? Okay, 1 mile is equal to 5,280 feet. Another way to say it is in yards, which is what? Somebody's a swimmer or a runner or something. How many feet in a yard? 3 feet equals 1 yard. Inches in a foot, everybody knows that. Who does not know how many inches are in a foot? Okay. Anyway, these are all things you can look up, but part of what distinguishes human beings from computers is that you get to use your intuition and think about things, and if you don't actually know some facts about the world, it's hard to use your intuition. So these are like ways to work your way around the facts. Anyway, here we've got this guesses about what this deformation is, and let's try and figure out what it is. Well, how are we going to figure it out? We've got this piece of wood. And it's got some tension on the end of it. And it's got some length. And it's got some width. And it's got some, I'll call it height. And what we'd like to figure out is what this delta is. It's some function of the length, the width, and the height. And what else? The properties. Certainly, if I, instead of passing out popsicle sticks or stirring sticks, I'd passed out pieces of steel, the amount of stretch, you wouldn't have been able to see it either, but it would have been different. Or a piece of rubber, it would have been different, bigger for a piece of rubber. Or a piece of spider silk. Amazing story on the radio this morning. Did anybody hear about the spider silk? They took a million spiders in Madagascar and collected their webs, 1 million spiders. And they took, one at a time, they drew the silk out of the spiders and did not hurt the spiders in doing it, and took the thread from these 1 million spiders and wove a tapestry. And it took, I don't know, 80 people 4 years to do it. It was a big project. Anyway, so spider silk would be different. Okay, now I'd like you to break up in teams of 2. You have 2 or 3 minutes. I would like you to tell me what this formula is. Okay, let me give you 3 solid minutes to work on it. break up in teams of 2 or 3. You can't just sit there. I want you to be there acting interactive.
That delta is the same as that delta.
You're running through it out,
Important variable T. Important variable T goes up there, right? You're trying to find a function that gives that I tell you the length, the width, the height, the tension, and the properties, whatever those are. You have to tell me what those are, and you want to tell me what delta L is. What's the formula that's going to tell it to me? Well, what can you say about that formula?
force equals.
Hi.
There's no escape. Go back in there.
I'm doing the real thing, the class puzzle and all this stuff.
Oh, okay. Cool.
You want to see what the puzzle is?
Yeah, sure.
Yeah, I'll show you their work. They got 2 or 3 minutes. I can show you how it goes.
Do we need to use all the variables?
You do not need to use all the variables. You get to use any subset you want, or if you have to invent new variables, bring them in. I give them each a coffee stir. I said you pull on it, it gets a little longer. In terms of the length, the width, the height, and anything else, give me a formula for how much it gets longer, and the tension.
All right. Cool.
Are you guys talking to each other?
Yeah.
It doesn't matter how much.
So it's just very
What is it?
take a long
Are you guys talking, thinking? What are you doing? Ask me a question if you have a question about the question. Yes? What? The usual assumption is that for small deformations, it's the same formula. But what for large, something else happens. It buckles. So until it buckles, it's the same formula.
But if they weren't
Vote A when you have an answer you're reasonably content with, or you really, and vote B if you totally give up.
Well, if it was the same force, maybe it would stretch more.
How you guys doing?
Thinking real hard.
So can we just do those?
Because the bigger it has more mass, so it wouldn't stretch as much as if this one. So how are we going to pack it?
Like,
You can show them zooming around the room, studying there. You can pan. These guys are good. You can zoom in on these guys.
remember when we did
So remember K equals 1 is K1 plus 1 of pizza. Price. Yeah. Price
there's no variables. Is this really simple? Are we all overthinking this?
We'll find out.
It seems like it's really simple. We're all
You got an answer?
5 okay.
What?
It's too simple.
You have an answer?
Oh, are we supposed to do it like for the 5 pound course or just?
I want a generic formula in terms of these variables.
Yeah, because tension is inverse. But
Okay, we're going to give you 1 more minute.
width and height.
So that's good.
Like, I mean,
But then we have to see. Yeah. You know what? Just thought. Oh yeah. Oh yeah. It's DL. It's the same as DL. That works. I don't know.
Okay, be quiet and let's. I want to collect formulas. So some collection of you, 21 of you, say you have formulas. Divide by 2 or 3. That's 10. I should see 10 formulas, or I should see agreement. So those of you who have formulas, tell me what they are. Raise your hand. Let's hear your formula.
T over K,
T over K,
where K is the spring constant.
where K is equal to the spring constant.
Good work.
Okay, next. Yes?
density times volume divided by K. Or density.
Density times length times
Density, just a minute, I just want one formula at a time. Or is it, you guys all the same formula? Density
times length times width times height upon K.
upon K, and K is equal to what?
The spring constant.
The spring constant. Okay, other formulas? Yes?
TL over KWH.
TL over KWH. And K is what?
Spring constant.
The spring constant. Where perhaps, as I don't know, as Bill Clinton says, it all depends on what "the" means. Which "the" we're talking about? Yes?
TLWH
TLWH over M. And M is equal to the mass. Okay. Any others? Yes?
T,
Wait a second. I got one in the front row here. Yes?
T over, T, L, N, L.
TL.
Ln, the Ln of L.
Length of L. Yes?
Over H with, H and with, density times gravity.
Rho G. Okay? Anything else? Yes?
We got T over K, where K is the spring constant as a function of L, W, and E.
K is a function of L, W, and H. Okay? Yes?
LWH over, like in parentheses, W minus delta W times H minus delta H. And then that whole thing minus L.
This whole thing minus L. Okay, anything else? Yes?
TL over WH.
TL over what?
WH.
And what's E? And where'd you get, what's that? The units are newtons over meters squared. Okay. Anybody want to vote for any of these things? Now, ready? A quick vote. Let's do without. Okay, clickers. 1, 2, 3, 4, 5. We're going to call this A, B, C, D, E. We want to flush your vote out of here in case. How do you flush your vote out of here? If you think it's one of the ones that's not listed in the first set, don't vote. A, B, C, D, E for these, don't vote if you think it's one of these. Because we're going to put an A, B, C on these two. Okay. How many vote for these? We got 15. 19. 1. 7. 2, 1. Okay, everybody vote for D or E. Just quickly vote for D or E. Okay, now how many vote for A, B, and C over here? 4, 1, and 16. Now how many voted for C because it sounds like he knows what he's talking about? No, wait, so, yeah. Looking over the teacher's shoulder during the exam. Okay. I find most of these kind of dissatisfying, and I'll tell you why. This is correct, because springs act like this, but it doesn't tell you what would happen if we changed L, W, or H, or we changed this from wood to steel. This one has some truth to it with this row. It is true that materials that are more dense tend to be more stiff. Steel is stiffer than aluminum, it's more dense. Aluminum is stiffer than wood, it's more dense. If you take two different kinds of wood, the more dense one tends to be more stiff. It's not a law of nature, but it tends to be true. This is not true, though. And now, why is this not true? Let's look at the width part of this formula. If I take two popsicle sticks or stirring sticks and put them side by side, I double the width. but each of them now has half the tension on it. So it's the same as one stick with half the tension. So when you double the width, we should have the stretch go down, not up. Okay, so we can cross this one off. This one has a t increasing with t. That's the linear part. That's right. Increasing with length. That's right too. Because if I put a tension on this and pull on it, it gets longer. If I put a tension on another one, it gets longer. And if I take the two and I tape them together, end to end, then each of them has the same tension, and we get the increase in length from both of them. So that if you have it twice as long, the length changes twice as much. We have the tension change from length change from here to here and from here to here, and the net length change is twice as big. So having this proportional tension, that's good. Having a proportional length, that's good. Having it inversely proportional to width, that's good because we put two side by side. Each one has half the load, so it stretches half as much. That's good, and height and width are just the same in this. They're both fatness of the thing. Then we've got this thing called K, which is the spring constant. And what do we mean by the spring constant? Somehow this catches the difference between wood and steel. So it's not the spring constant as in the constant of the machine, this thing with some length, width, and height. It's about a material property. So if you take this one and put K as some material property, something about the material, this is good. So I would give this an A+. What about this one? It's got this problem that is saying it gets longer when it's wider. Not true. The fatter it is, the less it stretches. And it's got the mass. If there is a dependence on mass, the density should be over here. Denser things tend to be more stiff. This is very fancy. Well, you have to watch. I guess just on technical grounds, we can rule this out right away. What happens if we put in that the tension, that the length is 1? So it gives 0. And by the way, 1 in what units? So it's a little bit offensive to have anything which is dimensional inside a log function or an exponential function or a sine function. It has to give the wrong answer because it's sensitive to the unit change. Okay, so this one we can cross off just on technical grounds here. Though there might be something sort of right about this log, and there is something sort of right about the log, but it's more advanced than we'll get to in this class. This one is right. I can't argue with it. Looks a lot like this one, doesn't it? It just doesn't. It's just that now we need to know what this function is for it to be useful. This one has the width in the wrong place, twice as wide and twice as fat. It shouldn't stretch as much. But it's got this other thing down here. And there's something right about this stuff too, but that's more advanced than we're going to get to in this class. So if you wrote that formula, just remember it when you get to things like Poisson's ratio in your later classes. And this one is absolutely correct. This is the same as this one. It's just got an E in there for K, and this is taking into account that which we know, which is now who announced that formula? So you cheated, right? You knew it already. You didn't just think to yourself, it must be called Young's modulus. It's a new idea. Some young person must have thought of it. Let's call it Young's modulus. Okay, so this one is the same as this one. So we know there's some material property here, K. And now we can figure out what the units of this property are. How can we figure out the units? Well, somehow this formula has to be all dimensionally correct. So let's just forget this E over here and stick with that K. Oh no, let's use that E. Why do we want to use the E? Because we don't want to confuse it with this K here. Okay, so the formula we have that we like, and let me just reason it out myself. Certainly, the change in length is proportional to the tension. Or in linear elasticity, our assumption that the more we pull on things, the more we stretch it. Certainly, it's proportional to the length, because if I put two in a row and I have the same tension, each piece stretches the same amount. Certainly it's inversely proportional to the width, because if I put two side by side, then each one will have half the tension and stretch half as much, and both of them stretch half as much. And same with this W over here. And certainly different materials will deform different amounts. So even though all these proportionalities are right, we'll have a different formula for steel than we will for wood, than we will for jello, than we will for rubber. And let's just call that proportionality constant E. That's the thing, that's the material property. So we've derived this formula by just saying it's got to be linear and it's got to follow common sense about area and height and so on. Now we have to say, what is this E? Well, we just invert this whole formula, and E is the change in length divided by the length. That's this thing divided by this, multiplied by the tension divided by this H and W. So I've just taken that formula and I've rearranged it. So what are the units of this? Well, this is units of length, this is units of length, this is units of force, and this is units of area. So the units of this thing, E, is force, the units of force, which has to do with mass and acceleration, but in real engineering practice, details. If you look through the lens on the other side, it's like invert. On the other side of the lens, where it's all inverted, that's what I meant. Okay. This is force divided by area. That's the units of this thing. When you write it this way, you can think about this a different way. You can think about this a little differently. This is this quantity here, L divided by delta L. If we go through to the other side of the lens, is L 1 over delta L over L. And this is a change in length per unit length. So as I take this stretch and stretch it, it's got a certain length and it's got a certain change in length. If I only look at the upper half of this, I draw a free body diagram of the upper half. How do I do it? I cut it with the chainsaw and I just pull on the upper half with the same tension. This part thinks it was back in this whole steering rod like this. So this thing has half the length and half the change of length. So the ratio of change of length to length for this piece with a given tension is the same as this piece. And in fact, any imagined piece in here, if I look at the length of it and the change of length between any two dots I put here, there's some length and some change of length, and they're all the same. So it's something intrinsic about the geometry in here, the change in length per unit length. And that quantity, the change in length per unit length, is called the strain. So this thing is engineering word strain. And it's unfortunately close in English language to this other word we're going to introduce now, which is this quantity here. This is the tension divided by the area. And all that came up in our reasoning about the proportionality was the cross-sectional area, not the width or the height per se. And if I look at this popsicle stick and I pull on it, there's a force per unit area. If I put two of them side by side, and pull twice as hard, I'll have twice the force and twice the area. So somehow the intrinsic measure of internal force is this force per unit area, and that thing is called stress. And these two words, as I said, are unfortunately similar in English usage, in English language, but in mechanics they're completely different. One is the sort of intrinsic internal load, which is force per unit area, and one is the intrinsic measure of distortion, which is strain. So that gives us this big formula that Young's modulus is this material property, is the ratio of stress to strain. And it's different for different materials. So if we look at wood, we get one number. If we look at steel, we get another number. And the metric gods are going to kill me for what I'm going to do now. But for steel, this is about 30 times 10 to the 6 pound force per inch squared, which if we do it in the SI system is about 2 gigapascals. Who knows what a pascal is? Raise your hand quick. Who does not know? Unit of pressure, it's a Newton per meter squared. It's very small. There are about 100,000 of them acting on you right now from the air in the room, all over your body. Very small quantity. So this is 2 billion of them is for steel. Now for wood, this goes down by about a factor of 30. So typical wood value is about 1 times 10 to the 6 pound force per inch squared. And in SI, we divide this thing by 30 again. So it's 2 divided by 30, which is 1 divided by 15, which is whatever it is, how many 100 million pascals. Okay, so what does this give us now for how much this popsicle stick stretched? This puzzle at the beginning of the class. So we have the stretch on this popsicle stick. So now the coffee stirrer. Coffee stirrer. The stretch of it is the tension multiplied by the length divided by EHW. We cooked up this formula, which I'm happy with. And now we need to plug numbers into this to try to figure out how much this coffee stirrer stretched. We have about 5 pounds force. We have a length of this coffee stirrer is about 5 inches. We have an E for this coffee stirrer, which is about 1 times 10 to the 6th pound force per inch squared, which is on this Wikipedia page, hidden behind the clicker, hidden behind the screensaver. But you can look up Young's modulus of wood, stiffness of materials. Probably, my guess is there 1,000 sites on the web where you can look up this number. And so that's the number for wood approximately. We have H and W for this piece of wood, which are about 0.030 inches and 0.150 inches, which I measured with my gadget before class. You can check me on that. Okay, so we want to see how much this coffee stirrer actually did stretch. We've got to multiply all these numbers out. Now, I've actually got them all in consistent units. All pound force is in inches. So what comes out of this, we cancel off pound force. We have an inches squared down here. We have an inches squared here that cancels. So what comes out of this is going to be something in inches, carrying all the units through carefully. Now, what's the number that comes out is 25 divided by 10 to the 6th multiplied by, here I have 3 times 1.5, which is 4.5. But to get a 3 and a 1.5, I have a 10 to the minus 1 here and a 10 to the minus 2 here. So I have a 10 to the minus 3 to get that answer. So I have 25 divided by 5, which is 5, multiplied by 10 to the, divided by 10 to the 3, which is times 10 to the minus 3. So it's 5 times 10 to the minus 3 inches is about how much this coffee stirrer gets longer when you pull on it. And what's that in, that's 5/1000ths of an inch. You want to know how big 5/1000ths of an inch is, how much this thing gets longer? Okay, you want to look at the gap here. You see there's no gap on this thing. I'm going to open this up 5/1000ths of an inch so you can see how big it is. We're looking for the gap right here. There's the gap. That's about how much it gets longer, that little sliver. Probably can't see it very well, can you? There's a little sliver there. That's about how much the popsicle stick gets longer when you squeeze it and pull on it. Now, I said there are ways that you can get this thing so you can see the deformation, and here's how. Hold up your popsicle stick. Another linear elasticity experiment you can do is you can hold it up by 2 fingers, and you can press it down with your chin. Okay, there are easier ways to do it. You can do it with fingers like that. But why do I do it like this is because that's the lab you're going to do this week, is this one with your chin. But you can simulate that with that. Now, this is also acting linear elastic. Somehow it's this same wood is making up a much softer spring. It's the same wood, the same properties. It's still acting like a spring with the force proportional to the displacement. But it's a different spring because it's deforming in a different way. So what's happening is when you bend like this, and this is a really hard exercise because it's so small to think about, but when you bend it like this, the top part of the wood is being stretched and the bottom part is being compressed. And the amount of that stretch and compression is on the order of 1 part per thousand. So one little fiber here that's a millimeter long is getting a micrometer longer, and one little fiber on the bottom of the wood, which is a millimeter long, is getting a micrometer shorter. And that teensy motion gets amplified by this lever to be visible in this big curve. So here you get that teensy deformation, absolutely teensy, 1 part in 1,000, but because of the geometry of this, it becomes visible because of this multiplication along the length. And that's what your lab's about today. Let's do 1 minute of questions and then end class. So this is a trick. To see it, it's like, hey, you said there's a trick. That's not a trick. That's dumb. But it is a trick, really, because when you do this deformation, something has to stretch and so on in the material. Just wait a second. Quick questions. Class too fast today? Raise your hand. Too slow today? So interesting that you can't stand it. Please be more boring. I just can't take it anymore. Okay. If you have any questions, comments about class, you can give them to me. You won't be punished in your grade if they're negative.